So let's take a look at this warm-up question. I picked this partly because I wanted to review from the last couple of topics that we've looked at, and because I want to use this to introduce the next topic, because there's a specific word in our question that is going to be relevant to this topic. So the question is, which is the activation energy of the forward reaction? And you're given a series of letters and quantities indicating different quantities. So what is the activation energy for the forward reaction? Leah? It is B. So when we talk about activation energy, we're talking about the amount of energy it takes for the reaction to get going. Yeah, Gavin? We're going to get to that in just a second. Great question. That is in fact the word that is important in this question. But just reading this energy diagram in ways that we have been doing so far, we've got our energy or enthalpy on the y-axis. We've got reaction progress on the x-axis, so beginning of the reaction on the left side, end of the reaction on the right side. Here is our reactants that we're starting with, and here's our products that we're ending with. And the activation energy is going to be the energy that it takes above the starting energy of our reactants to get the reaction started, to get over the hump, basically. So the size of the hump is essentially our activation energy. What is A? What is letter A? Yeah. That's the change in enthalpy. Good. It's a difference in energy between the reactants and the products. So Gavin pointed out the key word here that we're going to be talking about for the next week or two is that it says which is the activation energy of the forward reaction. So what's a forward reaction? Well, most of the reactions that we've been talking about so far, we've been writing it as, A plus B gives us AB or something like that, right? With a one-directional arrow, reactants on the left, products on the right, and we've made some assumptions that these reactions are going to completion. In the last unit, we talked about how long does it take for the reaction to finish. Rates of reaction from the start to the end, the average rate of reaction when the reaction is complete. So we've been talking about reactions as if they all are one-directional and go to completion, but that is not always the case. Many, many reactions are going to have a reverse reaction happening as well. And we typically draw this with a double-sided arrow that looks something like that. If you draw it with two full arrowheads like this, it's not wrong, but the convention is to draw it like this. Okay. What that tells us is that this is a reversible reaction.
That's the opposite of a forward reaction?
No. That's the opposite of a one-directional reaction. So the double arrow tells us that this reaction can go in both directions. Substance AB can decompose to become A and B separately, or A and B can combine to synthesize substance AB. Yes, Braden?
So I'm guessing, if you put in a certain amount of energy to get it back up to the top of that curve, right? Which way, if it's at the top of that curve, it could go down either way, right? Because it can go either direction. So then how would you know, why would all of the material go from, why would it just always be half and half? Why would it actually go transition from one to the other?
That is an excellent question, and that is going to be a big subtopic of this topic of equilibrium. How do we decide which way the reaction is going? How do we influence the reaction to go in one way or the other way? Yeah. Grace, do you have a question?
No, I can't.
Okay. Also, I forgot. Let's welcome Natalie to period 2. We had a, we had a little sob session this morning when you weren't there for first period. We all cried a little bit, but I didn't cry too much because I knew I was going to see you in second period. Not literally. Okay, do you want to stop session for? Just cry. Everybody just needs some catharsis right now. Okay. Yes, Grace. Yeah. No. Great question. So decomposition is the reaction, that would be in this case the reverse reaction, going from a substance made up of more than one element into its component elements, or not necessarily its component elements, but a subset of its component elements. Okay, so the classic one is, this is really also double-sided, but this is not a balanced equation, but the decomposition of hydrogen peroxide it's not going to hydrogen and oxygen, but it typically goes to water and oxygen gas. So that's, if you've seen or done the elephant toothpaste, that's what's happening. So the decomposition is a chemical reaction where we take a substance and break it down. Separation is something that we do with mixtures. So some things that are not chemically combined, but say if we filter something out, or we evaporate something, or the distillation that we did with the cherry Coke was a separation. We didn't actually do a chemical reaction to change the composition of those substances. We just boiled them at different temperatures. So that's an excellent question, decomposition versus separation. Decomposition is a chemical reaction. Separation is generally a physical process. Yes. There are reactions that are not reversible. So, yes, essentially, and that gets into some HL content, some Gibbs free energy, and spontaneous and non-spontaneous reactions, and it's stuff that I don't want to get into, but yeah, there is always some, and that I guess goes back to Braden's question of like, there's always some level of a possibility of a reaction going one way or the other. But there are a lot of reactions that we, under the circumstances under which we do the reaction, we think of it as a unidirectional reaction. That could be partly for a reason that I'm going to talk about in a second. If it's an open system, we can have unidirectional reactions where we're losing some of the products, then we can't have those products combined to go back into the reactant. So it depends on the circumstances of the reaction. Yeah, good question. Yeah. Because I didn't bother balancing it. It could, yes, one could balance it, yes. How would one balance that equation? Three on this side? We got to balance the hydrogens.
Putting them in the parentheses and multiply by 2. And that will be. What? Then that will be 6 on both sides.
Yes.
Yeah.
So 4 oxygens, 2 oxygens, 2 oxygens. Yeah. Right. Yes.
So if a forward or if a one-directional reaction is one direction,
Uh-huh.
then is a reversible reaction 2 directional?
Yes.
Okay. So there's
Yes.
only 2 directions that can go.
Yes, exactly. And that is what we're going to be talking about.
Do reversible reactions go to completion?
If they go to equilibrium, which is different from going to completion. That's exactly what we're going to talk about. Okay, so looking at this energy diagram again, if I'm telling you that this reaction is reversible, okay, that it can go either in the forward direction or the reverse direction. Looking at this energy diagram, what is the activation energy of the reverse reaction? Hank? C, yes, exactly. The difference between the energy of the reactants in that direction and the peak of the curve, yes. So is the reverse reaction exothermic or endothermic? Nick? It's endothermic because we're going from a lower energy level to a higher energy level. Are the products of the reverse reaction more stable or less stable than the reactants of the reverse reaction? Less stable because they're at a higher energy. Lower energy, more stable. Yep. Okay, so this is something that may, it won't often come into play, the energy diagrams in the equilibrium sense, but I wanted to include this question because it includes that forward, and you may have a question that asks you about the reverse reaction as some aspect of it. Now, what is the enthalpy change of the reverse reaction? It's still A. The enthalpy change doesn't change whether it's forward or reverse. That goes back to Hess's law from topic 5, whether the difference between the energies of the two sets of substances, the initial reactants and the initial products, is going to be the same whether we're talking about the forward reaction or the reverse reaction. The sign changes, exactly, yes. So the sign of our delta H for the forward reaction would be negative, and the reverse reaction would be the same number but positive. Yeah. Good. Right, it's the sign flipping, yeah. Of the enthalpy change, yep. Yep. Just the same way that when you flip reactions with Hess's law, you change the sign. It's exactly the same idea. Okay.
So the reverse reaction, is it always a higher activation energy?
No, because if I had if my forward reaction was endothermic, then the reverse reaction would be exothermic and would have a lower activation energy. Yeah, Hank?
Is there something that determines which side is forward and which side is backwards?
That's a great question. The convention is we draw the reaction with the initial reactants on the left and products on the right. And then you would consider that the forward reaction going from left to right on the energy diagram as well. So the idea is, if I'm going to start a reaction, I'm going to put a bunch of things together. Those things are my initial reactants. Yeah, good question. Okay. Okay, oh yeah. Quick cell phone policy reminder. We have a new policy. It starts today. Really for real, officially this time. I just want to talk about, for this class, when you come in and you're chit-chatting and whatever and doing whatever it is you need to do, that's fine. I am also often doing whatever it is I need to do, stapling the packets because the copier stapler was out of staples, whatever. In that period of time, especially before the bell rings, like if you were on your phone, it's not going to bother me, okay? I do want you to, at least by the time the bell rings, be looking at the board and thinking about whatever the warm-up question is, okay? If you finish the warm-up question and we haven't started class yet, and you want to check something on your phone, I'm not going to get upset about that because you have done the work that you were asked to do. And if I haven't started yet, then fine, get on your phone for a sec if you need to. But it is definitely when I'm talking. I mean, you guys are great. You guys are generally really great about being engaged in class and not using your phone. But if I'm talking, please don't be on your phone. If you're supposed to be doing independent work after a lecture, or if we start class with independent work, please don't be on your phone unless you have finished the work. Or obviously, if there's something's going on, I get it. But please try to be more intentional about your cell phone use versus just kind of having it out and around. And certainly, I understand how it is to just automatically reach for it whenever you're slightly bored or feel like you're just waiting for something. But let's try to reduce that. Okay. And I will tell you if there's a point where I'm like, yes, go ahead and use your phones. All right, so we're going to come back to graphs like this, so don't feel like you have to draw everything here. But essentially, I just wanted to kind of reiterate what we were saying with the energy diagram. So we've been talking about chemical reactions going to completion, meaning that all or almost all of our reactants are converted to products. We use the one-way arrow, but many reactions are reversible and don't go to completion. And they, instead of completion, they reach a point where they are at equilibrium. And the most common graph, we're going to be looking at a few different types of graph again in this topic, kind of like last topic. And some folks were a little bit lost with which graph was which and when we were going to use which one. So I'm going to try to be a little bit clearer about that and give you plenty of practice drawing and interpreting those graphs. But this is our typical rate graph, right? Concentration versus time, okay? And you're going to see a lot of this. But I want to point out a couple of things. First of all, when we're talking about equilibrium, we're usually going to have two things on the graph, not just one thing on the graph, one curve on the graph. And those two things are going to be our reactants and our products. So this blue-green line, teal, I don't know what you call it, that showing our reactants or showing our products? Reactants, how do you know?
Because it's getting depleted.
Yes, it's going down, okay? So our products are starting at 0. That's typically going to happen, but not always. You might have a graph where the products start somewhere that the product of the forward reaction starts somewhere that's not 0. But typically, we're going to put our reactants together, throw them in a beaker or a gas chamber or whatever it is, and they're going to start making products. And so the reactant concentration is going to go down, the product concentration is going to go up. The difference here is, notice that this blue-green line doesn't reach 0. Okay, so our reactants never go to 0. But they do reach a steady state. They reach an asymptote. Okay? And the asymptote, the steady state, is where what we call equilibrium. And you can see also that the products are increasing and then reaching a steady state, and we're ending up with flat lines, like we did when we reached completion in our previous kinetics graphs, but now our reactants are never going to go to 0. They're going to reach a new steady state, and that steady state is what we call equilibrium. And what's happening here, the reactants don't go to 0 because the reaction is two-directional. So some of the products are going to be converted into reactants at the same time that reactants are being converted into the products. Both the forward and the reverse reaction are taking place at the same time when we're at equilibrium.
Does that mean it just happens forever?
Yeah. Yep. Yeah. Until we change the conditions of the reaction. Yep.
Do they only happen at the same time once you reach equilibrium?
No, they're happening at the same time throughout. It's just that the rate of the reverse reaction is going to be 0 at the very beginning because we don't have any products. Right. And then as we start forming more products, the rate of that reaction is going to go up because the concentration is going up and driving the reaction backwards. Yes? The forward and the reverse reactions. Yeah. And what happens at equilibrium is that the rate of the forward reaction and the rate of the reverse reaction are equal. Okay. It's a little bit hard to wrap your head around this. So what I want to do is move away for a second from chemical reactions and start talking about physical changes, because we can also have an equilibrium with physical changes. I'm going to skip this. If you look at page 3 in your study guide, you have a picture something like this, or somewhat similar. If I take a flask and I put water in it, or a plastic bottle and I put water in it, and I open the cap and I leave it out, what's going to happen? Yeah, it's going to start evaporating. And the water vapor molecules are going to leave the space around the liquid water and come out and diffuse into the air of the room. There's always going to be some evaporation, because if you remember our Maxwell-Boltzmann distribution with kinetic energy and number of particles, we have something like this. We're always going to have some high energy particles in a sample, in any sample, regardless of the temperature. Just how many of them are at a higher energy is going to vary with the temperature. But there's always going to be some particles that are high enough energy that if they also happen to be at the surface, they can escape the intermolecular forces holding those liquid molecules together and evaporate, become a gas. When I first put, if I first put some water into a flask, the air right above the water is not particularly full of water vapor any more than the rest of the room is. So depending on how humid the room is, that's one of the things that's going to determine how quickly this evaporates, right? When I first put stuff in, at the beginning of this process, my rate of evaporation is going to be high, and my rate of condensation of water vapor molecules losing energy enough to come back down and become liquid is going to be pretty low, because there's just not that many water molecules, water vapor molecules, compared to the number of liquid water molecules. So at the beginning, we're going to see evaporation. And if I leave the system open, if I leave the cap off, then the evaporation is just going to keep happening, because there's always going to be a higher density of water vapor molecules right above the surface than there is in the rest of the room. And those water vapor molecules are going to keep diffusing out into the rest of the room, and eventually this is going to run dry. And the temperature and humidity of the room is going to affect how quickly that happens, but that's eventually what's going to happen. Now, if I put a stopper in it, again, at first we're going to have way more evaporation than we have condensation. But at some point, after enough molecules have evaporated and they have nowhere else to go, we're going to build up a high concentration of water vapor inside the flask that more of those molecules will lose enough energy, come back down, and condense into the liquid. And at some point, so at the beginning, if I put a stopper on this, if I fill this up to a certain level and I put a stopper on it and I measure the level of the water in the flask, at the beginning it's going to go down, because some of that water is going to go and become gas molecules. It's going to become water vapor. So the line of the liquid is going to go down a little bit. But at some point, it's going to stop changing, because there's going to be enough water vapor molecules that the rate of evaporation and the rate of condensation is going to be equal. That is equilibrium. That is the point at which we will not see any change in the level of the water or in the vapor pressure of the air above the water. Okay. Yes.
So equilibrium is, in this example, equal amounts of condensation and evaporation.
Yes. Yes, Braden. Oh, yeah. Speaking of water. Right. Yeah, I know. I'm a little bit thirsty too. So, again, this is just another picture of the same thing, but with a kind of reaction. It's not a reaction, but an equation for this process. So, in the beginning, we're starting with just liquid water, and some of it's changing to gas. But at some point, we get enough gas molecules that some of those gas molecules are going to go backwards and become liquid. And at some point, that rate, the rate of the forward process and the rate of the reverse process, are going to be equal. And that is what equilibrium is. So this is, we're going to revisit this again in the next slide, but it says there's no change in macroscopic properties at equilibrium. Macroscopic is the opposite of microscopic. Microscopic meaning something tiny, macroscopic meaning something big. So once we're at equilibrium, in this case, the water level isn't going to change. That's a macroscopic property. The volume of liquid is not going to change once we reach equilibrium, unless something changes in the conditions. Okay, so macroscopic properties can be things like the liquid volume. It can be a color change. It can be a variety of things that tell us that a reaction has happened or is happening. But those things are not going to be visible once we reach equilibrium, even though there is constantly evaporation and condensation happening. This is a dynamic system. Things are still moving, but we're not able to see a change by eye. Okay, so that is what they mean by there's no change in macroscopic properties. Okay. You might be asked to write an equation for a physical equilibrium, a change of state from one state to another. Make sure when you do that, you use the double-sided arrow and the state symbols. These are usually subscripts, not gigantic L and G. But if you draw it that way, it's fine. Nobody's going to take points off. Okay. Speaking of which, still page 3, I believe. You've got 3 questions here. You're being asked to write an equation for a system at equilibrium. Tell me about the rates of evaporation and condensation, and what could you look at to tell you that the system is in equilibrium. So go ahead and answer those questions. Yeah. Yeah, we're not there yet.
I already did that.
Okay, we're not there yet. We're going to talk about that tomorrow.
Oh, okay. Can I just ask a question
Yeah.
about it though?
Yeah.
So it says the concentration goes here, right?
Yeah.
But there's no what's the concentration for this? Because they just mean the symbol for the chemical.
No, they mean the actual concentration in the solution.
So to figure that out.
You would either give it or you would solve for it.
So in this case, but they don't give it for this. They just give 400.
So you would have to write these in brackets to show that it was concentration.
Okay. I see. All right. Thank you.
Yeah. Mm-hmm. Yeah.
It asks you what are fundamental properties. When I just say that, if you thought that it was accurate saying these properties, you would know that.
That is the key to that question, yeah. But what could you look at for that specific example?
It's asking.
Yeah. Yeah. Mhm. Yes.
When something reaches equilibrium, is it just the temperature? How is the temperature affected?
That is a great question, and we are going to cover that. That is one of the things that is going to affect the direction of the equilibrium. So yeah, we're going to get into that.
Well, when stuff is reacting,
Mm-hmm.
it creates even a tiny bit of heat, right?
Uh-huh.
So in the case of the water, it probably is making a tiny bit, but probably it's so little that we don't notice it.
Uh-huh.
Because otherwise we'd have infinite heat source, which is just not how it works. Because it's probably just so little that we probably can't even measure it, right?
Right. So there's the heat generated or absorbed by a reaction, and then there's us externally changing the temperature. And so we're going to talk about how those things interact.
Both would
Yeah.
matter, right?
We're going to talk about how those two things interact. Yeah. Come on. Just the first one. Yep.
Like the way the reversible arrow looks.
Yeah.
It's very satisfying.
Yes. Agreed. Great. So Ava has drawn our answer to number 1. Again, you might they give it to you in this question in the study guide that it's BR2, but in a paper 2 question, as that this might be the first part of a multi-part question, they might not tell you that it's BR2, and they might just say bromine liquid. A sample of bromine liquid is placed in a sealed flask, and you would have to know that bromine is one of our diatomic elements, one of the 7 diatomic elements. We talked about this briefly when we talked about the enthalpies of formation being 0 for these guys because they are already in their standard state. So you might be asked to know that this is BR2 and not just BR. But yes, that is exactly right. So what is true about the rates of evaporation and condensation of our bromine? Yeah, they're equal. The rate of evaporation is equal to the rate of condensation. And what macroscopic property could you look at to tell you that the system is at equilibrium? Grace? Sure. That's the easiest one. And how would you know by looking at the liquid level that the system, whether the system was at equilibrium? Yep. Yeah, so if the liquid level stays the same, we're at equilibrium in terms of this physical process. You could also look at, there are other things you could do. The liquid level is the easiest to measure, right? You could look at the color of the gas because the bromine gas is also a brown color.
Yeah, I knew it.
Yeah, so I heard you say something about that, yeah. So that's another thing that you could do to tell you, but that's a little harder to measure, but it is possible. So yeah, that's the key, is that the rates are equal, the macroscopic properties are not changing when we are looking at a physical process at equilibrium. Okay. So when we have chemical equilibrium, so now we're flipping to page 4 in your study guide, we have a chemical reaction, right? So it's not just a change in state, it's an actual reaction. But again, we have the forward reaction and the reverse reaction. So we've got in this case, we've got decomposition of hydrogen iodide is the forward reaction, and the synthesis of hydrogen iodide is the reverse reaction. And this is a reversible reaction, and we can look at the rates of reaction on a graph to figure out where the equilibrium is. And sorry, I should skip to this slide first. There's another type of graph, which is different from a concentration versus time graph, is reaction rate versus time. So make sure that you don't confuse these two graphs. So this is also on page 4. The rate of the reaction is going to converge to the same place, because by the time we reach equilibrium, the rate of the forward reaction, rate of the reverse reaction are going to be equal. Okay, so the forward reaction is going to start out high because all we have is the forward reactants. We've put a bunch of things in a beaker or in a cylinder or whatever, and the forward reaction is going to start off quickly and then is going to gradually decline. The reverse reaction is going to start at 0 because we don't have any products yet. But as we build up more products, that reaction is going to get going. And then at some point, they're going to meet at equilibrium. So if you see a graph like this, the equilibrium happens when they meet. So everything after the point that they meet is considered, the reaction is considered to be at equilibrium. Okay. But we can also look at a concentration versus time graph and determine equilibrium, because we can look at where it flatlines. And again, the reactants and products are not necessarily going to, the concentrations are not going to end up equal. Okay? But they are going to be steady state. So we can have these lines crossing, we can have them not crossing. There's lots of ways that the concentration lines could end up. Okay, as you can see on page 5 of your study guide at the top, there's a couple of different ways that we can look at this. Yes?
Does them crossing indicate anything?
No. I mean, it indicates something about how the, like if I have them, let me do this, redo that. Something like this versus this. We're still at equilibrium here when they're the same. The point of crossing is not significant in and of itself. What this is telling you is that at equilibrium, we have a higher concentration of products than we do reactants. Yes? No such thing. Yeah, no. Hold that thought, and we'll talk about it tomorrow. Yeah.
Maybe I did. What's to you? A lot.
You're welcome. All right, just gonna leave that there.